To wrap up subtopic 11.1 on electromagnetic induction, we're going to have a look at how an EMF is induced. So just to reiterate, the equation that we use for EMF is negative n delta phi delta t on delta t. And if you recall that the value of phi is given by the magnetic field strength and multiplied by the area over which that magnetic field is acting. And so we can expand the expression for magnetic flux to be B times A. So for an EMF to be induced, as the equation suggests, there needs to be a change in flux. And what we'll be looking at here is different ways to create a change in flux. And some of the ways that can be done here, we'll have a look at a few examples, not a whole coverage of every possible example, but just some ways to get your head around how that applies in a few different scenarios. And basically it comes down to linking back to this equation of delta phi on delta t. And so we'll look at the first example. We've already seen this one really, but I'll do it in a slightly different way. So the first way that we can induce an EMF is by changing the area of the coil. And so what I'll do here is we'll start out with a coil. We'll deal with a square coil here just because the area is a little bit easier to analyze. And imagine we've got a magnetic field that's directed into the screen, as represented by the crosses here. And we're going to keep that magnetic field strength the same, so at some later point in time, so I'm going to still have that same magnetic field. And at some time later, so think of this as being a transition between two states, so we'll indicate this is after delta t, the size of that coil has now decreased. So given that the coil is now smaller, it means that the flux through that area is going to have decreased because the area itself has decreased. So in that case we'll see an EMF being induced. The second way that we could induce an EMF is by changing the magnetic field strength or changing the magnetic flux density. And make sure you are comfortable with both of those terms. They can be used interchangeably. So again, if we start off with our coil or our loop, and at some later stage we'll see that loop is still the same size, so we're not changing the size of the loop at all, so that's staying now with the same area. Instead what we're going to see is that we'll start with the same conditions as the diagram above. So in this case magnetic field strength will increase, so we would now see more field lines in that area. So you can see here we've got a greater density of the magnetic flux, and as a result again we would see that there is a change in flux that's occurring in that scenario. And the third situation is if we actually change the direction or change the orientation of the magnetic field. So keeping in mind that a magnetic field is a vector quantity, so we can change the direction and therefore have an effect on the change in flux. And again we'll start off with the same scenario as above, a loop that is not going to change size, and again at some later point in time between the two, so delta t, we're going to see that initially the flux would be through the loop, into the screen, because the magnetic field is directed into the screen, and at some later stage that has then flipped by 180 degrees, so now with dots to show that the flux is coming out of the screen. So in that case we'll see that there is a change in flux due to the change in orientation of the field. The strength of the field hasn't changed, it's just the direction that's changed. So that gives us an indication that an EMF is going to be induced. The other thing that we need to consider is the direction of a current that would flow due to an EMF being induced. So to determine the direction of the current, we can refer to Lenz's law. I'm going to expand Lenz's law a little bit here to provide a little bit more of a bit more detail on another way to consider how to determine the direction using Lenz's law. So in referring to Lenz's law, I'm going to expand the explanation that we indicated in an earlier video. We start off with the same idea, that the induced current will flow in a direction, induced current, and previously we've said in a direction that will oppose the change that caused it. We're going to expand on that idea and identify that it's going to produce its own magnetic field. So the magnetic field that is induced by the current opposes the change in flux that caused it. So we're not just saying now that it's the change that caused the current to flow, it's specifically the change in flux that induced the current. So if we go back and have a look at these three scenarios, I'll just notate them very briefly. We can have a look at them in more detail. It is a pretty tricky concept to get your head around, but hopefully we'll be able to expand on this where we need to. So if we look at the initial condition here for the changing the area, the flux would be directed into the screen, given that the magnetic field is directed into the screen. The area is large, and so it'll be a large flux into the screen. On the right hand side over here, we have that the flux is now going to be smaller because the area is decreased. So the change in flux is actually going to be directed out of the screen. So that's the first point to identify, that delta phi is out of the screen. So we first need to identify what the initial flux was, what the final flux is, and notice in this case that delta phi is actually opposite the direction of the B field. So the direction of the magnetic field doesn't guarantee that you'll be able to figure out the direction of flux as being in the same direction. So it's an important point to note there. And because that change in flux is out of the screen, the current will have to be clockwise. And the reason for that is so it produces its own magnetic field that will be directed into the screen. So producing its own magnetic field into the screen to oppose the change in flux. So there's the first one. For the second one, we have a slightly different scenario. The change in flux now is actually going to be into the screen. We start off with a flux on this side that's into the screen. We then end up with a stronger magnetic field into the screen. So the change will also be into the screen. So here delta phi is into the screen. So I is now going to be anti-clockwise. Now, in order to identify the direction of the current, you can use the right hand screw rule here. So in this case, being anti-clockwise, the magnetic field that's induced will be out of the screen. So if you need to check that to make sense of it, right hand screw rule allows you to figure out the direction of the magnetic field inside the loop given the direction of the current, and so you can identify the direction of the current that's required. Finally, the changing the orientation of the magnetic field. Should also mention here that could be the magnetic field, or it could actually be the coil that changes orientation. So if you flip the coil around 180 degrees, you'll get a similar sort of effect. In this case, initially the flux is into the screen, so because we've got the magnetic field directed into the screen, and then on the right hand side it's out of the screen. So in that case, delta phi is also out of the screen, and similarly to before, I will now be clockwise, or will be clockwise again. And again, that's so that so its B field is into the screen. So there's a few examples of how to identify when an EMF is going to be induced and the direction of the current that will flow when the EMF is induced. Lots of different ways that can come about. We will use that moving forward when we start to look at power generation, so things like generators. Makes it easier to think about the direction of current flow if you're also aware of the change in flux that's occurring in those sort of scenarios.